All right. So we are going to go into electromagnetic induction. We previously have already settled the part on electromagnet. Okay, so we're going to go into electromagnetic induction today. So what I've mentioned previously, okay, in the chapter of electromagnet, we are talking about either using electricity to induce magnetic field. Okay, if we use electricity to induce magnetic field, we will definitely just a quick summary, right? So how do we actually identify its electricity to induce the magnetic field? Well, in the circuit, okay, in the circuit there is power supply, okay, there is current flow, and then there is also charge flowing. So this charge can either be an electron, or it can be electron which is negatively charged, or in later on when we go into electronics, we know that another one would be positive charge. Okay, it's very important that you understand that electric field to induce magnetic field, it's not only regarding current flowing. Current's definition is the rate of charge flow. So the charge flowing means there are negative charges flowing. There is also positive charge flowing. So you have to understand that this can induce magnetic field as well. So when it induces magnetic field, all right, there is going to be interaction, okay, between the magnetic field from permanent magnets and also the one created from a current carrying conductor, right? Which means wire, all right? The current, there is wire, there is current flowing into the wires, all right? There will be interaction, and that particular interaction is what we know as the catapult effect or the catapult field. Okay, then if it's electricity to induce magnetic field, we will have to use our Fleming left-hand rule. All right, so that is what we have already learned previously. So right now we are actually going into the other opposite direction. We are actually using magnetic field, okay, permanent magnetic field to induce electricity. So how do we identify if it's permanent magnetic field to induce electricity, which in what we call right now the electromagnetic induction? All right, there is no power supply. So if there is no power supply in the circuit, which means there's no battery, there's no extremely high tension voltage or whatsoever, there's no current flowing at all in the circuit. All right, so there's no power supply in there, and then normally there is a resistor. We could have a galvanometer. All right, we can also have a light bulb or what we known as load in certain books. Okay, so over here, when permanent magnetic field is used to induce electricity, there will be induced EMF, right? Induced electromotive force. There will also be induced current. Okay, so in order to identify the direction of current flow, we will use Fleming right-hand rule. Okay, so this is how we identify whether are we going to be, is it electricity inducing magnetic field, or is it magnetic field that induce the electricity out? Okay, so let's go to this slides that I've already sent to all of you previously. Now, electromagnetic induction, the definition is the production of electric current by a changing magnetic field. I'm choosing to use these notes more because I noticed there's not much of a stuff or definition that comes from the textbook. So that's why I choose to use this PowerPoint slides that I've already sent to all of you previously. All right. If I am having the Google Meet is hang or anything, just send a message because I'm using another tablet to overlook my whole entire Google Meet. Okay, so over here, all right, so how does induced current is being produced? Okay, so I'm going to use a simulation right now. Okay, for example, right now I have a north and south magnet. All right, this is a coil, a solenoid, and then it's connected to a light bulb. So there's no power supply in this circuit. When there's no power supply, we know that we're going to be using the magnetic field, the magnets, to produce out electricity. So I'm going to show you the magnetic field lines. So if I were to bring this magnet closer, you would see that at this light bulb, all right, you can actually see that the light bulb actually lights up or not. See? So, and if you notice one thing, if I were to move like this, it's not much of current that the current that passes through the light bulb. Now, how do you identify when there is current flowing? All right, it will actually light up. Right, when there's no current flowing, then it won't light up at all. So if let's just say, for example, where's my mouse? Okay, if this line is very, very little. You see? There's only one magnetic field line. It's very far away from the actual magnet. So when the magnetic field is very, very weak, it's not going to induce a lot of current out. But when I bring the magnet closer to the coil, all right, and when I go closer in, you will notice that the current induced is actually much more higher. Okay, whether is it the north or the south, it can induce more. So what is the difference? The difference is actually the magnetic field lines. All right. The magnetic field lines that this conductor cuts through. I'm sure you have already seen the word called magnetic flux. Magnetic flux is actually the number of magnetic field strength per unit area. So very quickly to show all of you right now. So I'm going to take this. Okay. So let's just say at this corner, okay, so how come it's not? Okay, simulation doesn't allows me to do so. So I'm gonna use back my old method. I've forgotten I'm using this simulation. Okay, so what does magnetic flux actually mean? So if I was to take a cross-sectional area, all right, at this position, all right, at this position, okay, the number of magnetic field lines per area is actually stronger compared to the magnetic flux at this area. All right, area B, this is B. Area B has very few magnetic field lines, so the magnetic field strength is weaker. The magnetic field strength or lines per unit area is actually the word magnetic flux. So when there's more magnetic flux that is being cut through by this coil or this conductor, then it will induce more current out. Okay, so if you look back at this one again. Uh, okay, well, that render for a while first. Okay, how induced current is produced? It is produced when there's a relative motion between the conductor's coil or the magnetic field lines, which means that there will be either you make this coil move, all right, the wire move or the conductor move or solenoid move, or you move the permanent magnets. So the more the lines, the magnetic field lines that the conductor cuts, the stronger the induced current that will be produced. So if you see over here, this is very, very weak, right? Why? Because it's very far away from the permanent magnet. The magnetic field lines that this conductor cuts through is very little. But if I were to move this here, you would see that the light bulb keeps on lighting up, right? The main reason is because there's more magnetic field lines here. the conductor cuts the magnetic field lines even more compared to the initial position like this. All right. So if it cuts more magnetic field lines, it will produce more induced current. Okay. So I hope that clarifies. And as usual, if you have any questions that you want to ask me halfway I'm explaining, just type in the chat box. All right, so the relative motion of the conductor across a magnetic field can be produced using two methods. One, all right, as you can see over here, number one, check the circuit. This is a wire that is connected to a galvanometer. In a short while, I'll explain regarding a galvanometer. And then after that, there is a permanent magnet. There's no power supply. So this is obviously a magnetic field inducing electricity, all right, inducing current out. The second situation, again, you have a solenoid connected to a galvanometer again, and then there's a permanent magnet. So this one, there's no power supply, so it's again magnetic field inducing electricity or inducing current out. Okay, so it's either we move the permanent magnet or we move the wire. All right, so then they will induce a current out. So what is galvanometer? Okay, let's see. Let me cross-check the textbook. Do they say anything about the galvanometer? No. So I'm going to explain very briefly what is a galvanometer. I'm sure all of you actually heard the word of ohmmeter from your RBT. And then we have voltmeter and also ammeter. Ohmmeter is actually to measure the resistance that we don't really measure the resistance in physics already. All right, voltmeter is to measure the voltage or the potential difference. Ammeter's main purpose is to measure the current. Now, all these three ohmmeter, voltmeter, and ammeter device actually comes from galvanometer. Okay, so ohmmeter, ammeter, and voltmeter, the scale of the zero is actually at the side. So when it's resting, there's no electricity passing through, right? The arrow will point to the zero, which is on the left-hand side. And then the reading scales normally depending on the situation, either 1, 5, 10, 20, or so on and so forth. But galvanometer is slightly special. Galvanometer is actually the basic of all three ammeter, ohmmeter, and also voltmeter. Galvanometer 0 is actually in the middle. Please do take note. Galvanos ohmmeter 0 is actually in the middle. The main function of a galvanometer, it has scales at the side. 1, 2, 3, 4, 5. All right, and the other side 1, 2, 3, 4, 5. The only difference is towards the right is positive, towards the left is negative. Galvanometer's main purpose, apart of showing the magnitude of the current flow, which is also ammeter, galvanometer has one main function comparing to the others, is to determine the direction of current flow. All right, to determine the direction of current flowing. Okay, now last time in KBSM syllabus and in most reference books right now that I've noticed, I'm talking about KBSM textbook. All right, in KBSM textbook, the galvanometer follows the direction of current flowing. But then for your KSSM syllabus textbook, which I will follow, is actually showing where the current is coming from. All right, so you have to take note about this because I'm sure most of you won't really go and use the textbook. Most of you will actually go and use the reference books to do your studies anyway. You will get the problem here, and you did face this problem in your paper 1 and your paper 2 trials the other day. Why? Because KBSM textbook and the reference book, they did not notice that inside KSSM textbook, your Form 5 textbook, the direction for the galvanometer is actually showing where the current is coming from. All right, the previous textbook is showing where the current is going to. All right, there's a difference over there. Okay, so where we follow, where the syllabus is follow, where SPM is going to follow, we'll follow back your current textbook. okay, which is where the current is coming from. All right, so please do take note on this situation. All right, later on when we discuss certain questions, I want you all to take note of that. Okay, so over here, all right, so once we have already got that clarified, okay, so we are going to explain some stuff first. Each time a straight wire cuts through the magnetic field, all right, the permanent magnet moves towards the solenoid, a current is induced in the coil, and a deflection is observed in a sensitive galvanometer. So the current detected by the galvanometer is called the induced current, right? Electromotive force that is produced is called induced EMF. Because in chapter 3 in electricity, in order for current to flow, you need to have a potential difference. So over here, the previous chapter 3 and the previous electricity inducing magnetic field, there is a power supply over here. But in electromagnetic induction, there's no power supply. There's only relative motion between the wire or the solenoid. So when the wire or the solenoid cuts the magnetic field lines, it will induce a current out. All right, so when there's a current being induced, definitely there is a source, an electromotive force. All right, so that's why it's called the induced electromotive force. Okay, so first thing first is actually electromagnet induction in a straight wire. So straight wire, I remember I need to go back to your textbook. Okay, so over here, all right, so I'm gonna use this picture. Back to the solenoid, I would suggest you guys on one thing. Uh, get a piece of paper, get your pen, all right? Don't just look and stare, because in order to understand electromagnetic induction, you will need to use your Fleming right hand rule. All right, so it's very important that you get a paper and pen and you scribble whatever that I'm scribbling in front of the PowerPoint slides right now. Okay, so right now they have permanent magnet and the magnetic field is moving from north to south pole. The wire is actually being moved above. Okay, so let's have a look over here. Okay, so I'm gonna draw as though that my eye view is looking from the front. Okay, so if I look from the front, I have my north pole point at the right, and then I have my south pole on the left. And then after that, this is the wire, all right? A single straight wire, and this wire is being moved to the top. For Fleming left hand rule, the wire, the force when we use FBI for Fleming left hand rule, all right, the force is actually what we determine later on. But for induced current, all right, we use Fleming right hand rule because there's no power supply. But right now, when we want to determine using our Fleming right hand rule, it is the induced current that we are going to determine. So please make sure that you draw this picture on the right hand side that I have right now on a piece of paper, put it on your table. Don't just stare, because I'm going to ask you to move the paper so that in exam you understand how to determine the direction of the induced current. All right. So I hope that you have really drawn that while I was explaining just now. So right now, okay, we have the force. The wire is being moved by the question. The question itself will tell you whether the wire is being moved up, moved down, to the left or to the right. Okay. So here the wire is being moved up. The magnetic field is pointing from north to south. So that's our B. Okay. So I hope you're ready. With this paper on top of the table, okay, what I want you to do is stick out your right hand, Fleming right hand rule. So we have the force, then you have the magnetic field, and this one would be the direction of the induced current. Okay, so do take note. Hope that you guys are actually seeing my face and my hand instead. So the thumb will show the direction of the force. The pointing finger is actually from north. This is here is north, pointing towards south. And then for the middle finger, all right, it's actually the induced current direction. So if, let's just say, when you do and you identify the middle finger is pointing towards you, it actually means that the induced current is coming out. All right, because it's pointing towards you. But when you determine your Fleming right hand rule, and you see the back of your palm, all right, you see the back of your palm, and the middle finger is actually pointing away. So this is actually current entering the paper. All right. So how am I going to determine? I hope that you guys are ready. So Fleming right hand rule. So put the thumb pointing upwards. All right. That's the direction of the force. Put the let's just say I draw the question here. Okay. Let's just say I draw my question over here already. So my force is actually pointing upwards. Okay. And then after that, my magnetic field is pointing towards the south. And finally, the current, I see that it's actually pointing towards me. So if it's pointing towards me, the induced current would be a dot over here. All right, the induced current would be a dot. So what I'm seeing is that the induced current, all right, the induced current is coming out of the paper. So I hope you guys actually got that. All right. So if it's coming out of the paper, which means that my current flow is actually this way, because this is the point of view that we're having looking at. So we see the arrow coming out. So you see the dot. So the current, when it actually moves like this towards the galvanometer, I'm not going to talk about the galvanometer yet. I'm going to say about the current flowing, the induced current flowing. Then you see that the current is actually moving this way. Okay, so when it's moving this way, galvanometer, it will show the direction where the current is coming from. So the current is actually coming from the left hand side. So if it's coming towards the left hand side, that's why it's deflecting towards the left. Okay, so that's the reason why the galvanometer deflects towards the left. Please be alert, all right? Because even if you don't know where the galvanometer is looking, look at the zero. The zero is located in the middle, all right? So the pointer is deflecting towards the left hand side. Means the current is coming from the left going towards the right. Okay? So I hope that is okay with you guys. So again, galvanometer is pointing to the left, indicating that the current is coming from the left. Or in another words to say, current is entering from the negative terminal. Why I say negative terminal? Because the black color part is negative. This black color part is negative. Okay? And then going towards the positive. Okay? But normally they will just ask you, where is the pointer of the galvanometer deflecting? Towards the left or towards the right? That is normally what they will ask you lah. Okay? So just remember that pointing towards the left indicating that the current is coming from the left, not current going towards the left. Okay? So please be alert. If you have your reference books in front of you, you would notice this difference inside your reference books and also in the textbook itself. Okay. So let's see. Is there any question that I can use? Tada question. Okay. So I'm going to go into a solenoid right now. Just now is a straight wire. Right now is a solenoid. Now, electromagnetic induction in a solenoid, how does it happen? Okay. Number one, we have a solenoid, we have a galvanometer, we have the magnet coming in. So in electromagnetic induction, a part of Fleming right hand rule, you know that there's a Faraday's law and a Lenz's law. Faraday's law will tell you the magnitude, Lenz's law will tell you the direction. All right. Lenz's law will determine the direction. Faraday will tell you how whether to increase or decrease the induced current. But do take note, Faraday's law, even though it determines the magnitude, you do not need to learn any formulas for electromagnet. The only formulas that will come out is later on in transformer. Okay, there's no formula for SPM level for electromagnetic induction. All right, so over here, all right, electromagnetic induction in a solenoid, when I take a magnet and I move through the solenoid, it's actually similar to this simulation. When I take it and move it into the solenoid, what happens that we see is that the galvanometer will deflect, or the current will actually deflect. So let's just say if I change it to voltmeter, all right, assuming that's a galvanometer. Why? Because it's in the middle, all right? Voltmeter normally is on the left. So when I actually move it away or bring it in closer, you would actually notice that it's actually deflecting either towards the left or towards the right. So when I bring it in, it goes to the left. When I move it away, it deflects towards the right. Number one. Number two, observe if I go in slow, the deflection is very little. All right. When I move away slow, it deflects towards the positive or the right, very small also. But if I go in fast and I move away fast, the deflection is actually higher. So what does this mean? This means that electromagnetic induction would be faster, would be stronger. The induced current is actually much more stronger if you move the magnet or the conductor faster speed. If you go slow, the induced current is actually very little. All right. If you move away slow, it's also going to be very little. But if I move fast, okay, it's going to be a lot. And then after that, you will notice one thing. If I put it in the middle, I don't move it at all, nothing will happen. Why? Even though it's in the middle of the magnetic field, magnetic permanent magnet is in the middle of the solenoid, its magnetic flux is a lot, but the thing is, there is no cutting of magnetic flux when the conductor and the permanent magnet is not moving. So you need it to move. There's a change in magnetic field. All right. Then only it will induce current out. Okay. So this is what this slide is talking about. If we were to push it in, the galvanometer will deflect. If the galvanometer is held stationary in the middle, nothing will happen to the galvanometer. There's no induced current, no induced EMF at all. But when you move the magnet bar out, the galvanometer will deflect the opposite direction. All right, so this is actually what the activity in the textbook is talking about here. All right, this is what it's talking about. So let's us right now using Lenz's law to determine the direction of the magnetic field. All right, we're going to determine the direction of the magnetic field right now. So I use the Fleming right hand rule to teach you guys. Do you guys still need me to talk about this portion? Yes, no? Knock, knock. Do you still need me to discuss regarding this? I discussed it just now already. Still need me to explain regarding this part?
No need, teacher.
No need. What about the rest? Rest okay? All right, good. Okay, so I'm going to go to Lenz's law, and Lenz's law is where we're going to discuss regarding the solenoid. And please do one thing. Do not memorize the direction. All right, if you memorize the direction, then I can say kantoi later. All right, Lenz's law. Lenz's law indicates the direction of the induced current in a magnetic field, in a solenoid, in such a way that the magnetic effect that is being induced out will always oppose the changes producing it. So when the relative motion between the magnet and the solenoid is coming together, all right, like this, If the solenoid and the magnet is coming together, the produced currents will actually oppose. Okay, if it's moving away, it will actually attract. All right, so you see, when the relative motion between the magnet and the solenoid comes towards each other, the polarity of the ends of the solenoid facing the magnet has the same polarity. In a short while, I'll explain this. All right, if it's moving away from each other, it's opposite polarity. Now, in order to explain this, so I'm going to explain using one analogy. I'm going to talk about standard one. Okay, I'm going to talk about standard one and I'm going to talk about form five. Standard one, normally when you get to a new school, you sit at the table, the next table is actually empty, and then another person comes here, and the teacher actually asks that person to sit next to you. When this thing happens, when initially the person doesn't come, you are very comfortable sitting at that table by yourself. But if a new student comes in and the teacher asks that student to sit beside you, what will happen first? You will initially scan through that person and you will be very, very reluctant for that person to sit beside you. General cases, normal cases, most cases are not all. You will normally look at the person and scan through that person, and then you will try to analyze, are you going to be good friends with this person? Are you going to be comfortable with that person? And then when the person tries to talk to you, you're like, I'm not going to talk to that person. So what does it mean? All right, it means that when something new comes, all right, something or someone new comes, you will initially reject, right? You will initially reject. But then after a certain period of time, you're already comfortable with your friends, all right, from standard one until standard six, and then from form one, you so happen to be in the same school, form one until form five, still the same school, still the same class, still the same partner. Got this situation in your class. So if this thing happens, all right, I'm sure that you are already very comfortable sitting next to your partner for so many years. But then reality comes, SPM. You and your partner has been sitting next to each other for such a long time, but there's one thing obvious. Your interests and your partner's interests are too different. All right, very different. So after SPM, after March 2023, you would notice that you have to go to a local college that let's just say you are planning to go to Taylor's, for example, and then your partner, your friend plans to go to Sunway, even though it's still in Subang, but it's going to be two different schools already. All right. So what happens is after SPM ends, you know that you need to go separate ways. But in order to bring back the friendship, you will start asking to meet up. All right, you would go to the cinemas, you will meet up at Sunway Pyramid, all right, you'll go for movies, you'll go for cafe hoppings or go for window shopping or whatsoever. You are supposed to be separated to two different schools, but you both of you still have the intention to pull back your friendship, all right, to make your friendship closer. So in this situation, when you are going separate ways, okay, when you are going separate ways, what you will do is you will try to attract each other back. Attract each other and to maintain your friendship. Alright. So this is it's a very normal situation. So what does this have to do with electromagnetic induction? Those who have learned, you would have really start to relate. So what does this have to do with electromagnetic induction? So let's just say I have a solenoid right now. I have a galvanometer. And this solenoid is linked. Okay. It's at it's a very comfortable zone right now. Comfortable zone, which means the arrow is actually pointing to the zero. And then suddenly a solenoid comes. A permanent magnet comes. Let's just say North Pole. When North Pole comes towards the solenoid, Same thing like this. Something new or someone new comes along, you will initially reject it. So if the north pole of the permanent magnet come towards the solenoid, question, answer in the chat box. What should the solenoid do to create a polarity here in order to oppose or to attract the incoming north pole? When north pole of the permanent magnet approaches the solenoid, should it attract or should it repel? Attract or repel? Alif say repel. Some more? Min you also say repel? Repel. Yes. Alright, because when something new comes, you're not comfortable, you will reject the thing first. So in order to reject north, this solenoid will create a north pole here. All right, when this is north, the other side will be south pole. This is a magnetic field that is produced by the solenoid in order to reject the incoming north pole. So when this happens, all right, this is north and this is south, because there's so many solenoids, we can't use the Fleming right hand rule anymore. So what we do, we use the right hand grip rule. So again, if can, draw out this situation, or if you are using your monitor, your screen, your laptop or your desktop, right, or your handphones, please take your hand, let the thumb point towards north pole. All right, why? Because one situation, in a magnet, all right, the magnetic field is coming out from north, entering south. So when you put your thumb, the thumb should point towards the north pole. All right. So when it points towards the north pole, you would notice that your fingers in front here is actually curling down. Your fingers is actually moving down when it's pointing towards the north pole. All right. So when this happens, the current is actually pointing, the induced current is pointing down. When the induced current is pointing down, it will actually go this way. All right. So can I ask one question? Should the galvanometer deflect towards the left or towards the right hand side? Should the galvanometer deflect towards the right or towards the left? Now that the induced current is coming down this way. Okay, Alif and Mingyu have already responded right. So yes, correct. The galvanometer will deflect towards the right hand side. Why? Because the current is coming from the right, ma. So the galvanometer will deflect towards the right hand side. Okay, so I'm gonna try to do one thing. Now, looking at this, all right, looking at this, I'm gonna draw another solenoid. Okay, so please do try to learn how to draw the solenoid together and then to analyze together. Okay, so this is north, this is south. I have a galvanometer, and again, right now, the north is going towards the left, towards the solenoid. Quick question. Will the galvanometer deflect towards the left or towards the right? Can you predict? Will the galvanometer deflect towards the left or towards the right? Edmund say left. Wait, Okay, so we have left, left, left. Okay, so let's see. When the north comes, the solenoid will produce north, and here would be south. With our right hand grip rule pointing towards the pointing towards the north, the fingers are actually coming down in front. When it comes down in front, that is my direction of the induced current on the solenoid. So current going this way, so my galvanometer will deflect towards the left. What's the difference? Both picture, north is coming in. Both picture, north is coming in. Both of it, the solenoid creates a north pole on the right hand side. But what's the difference that causes the solenoid to initially deflect towards the right and now it deflected towards the left? The biggest difference is how the solenoid was being turned. Yes, the coil. Alright, initially this coil is actually moving from the front going towards the back. But the first question, the coil went towards the back, then only come back in front. Okay, so it's very important for you to understand which direction of the coil or the solenoid is moving. Okay, so that will determine whether it's moving up or moving down. Now, so if it's moving away, let's just say, for example, let me analyze another one. So for you guys to clarify that before I proceed. All right, here I have a galvanometer connected to the solenoid. And then right now, changing the question, south is moving away. All right, south is moving away. So my question is, at this side, this solenoid part that is closer towards the magnet, the south is moving away. What should be created at this corner of the solenoid, north or south? Sarash said south. The rest? Refer back to the analogy that I drew just now. Right now, south is moving away. So is it standard 1 situation or form 5 situation? South is moving away from the solenoid. It's supposed to be a form 5 situation. You are going separate ways already. So in order to, when you're going separate ways, you will try to attract each other to maintain your friendship. So when south of the permanent magnet is moving away, the solenoid wants to maintain the south pole closer to the solenoid. So in order to maintain its position, the solenoid has to induce a north pole. Why? North and south attracts each other. All right, north and south will attract each other. That way, it will actually pull back the south, ma. All right, so this is south here. This is north. This is the induced south. Again, it will be going downwards. So the galvanometer will deflect towards the left where the current is coming from. All right, so this is what happened. Sarash, are you okay? Okay. Now, so you see, when the magnet is moved towards the solenoid, whether the magnet move towards the solenoid or the solenoid move towards the magnet, it's still the same. As long as it's getting closer to each other, they will reject each other with same polarity. So induced current produces a north pole to oppose the motion of the magnet coming towards the solenoid. But if the magnet is moving away or the solenoid is moving away, all right, this is north pole. So the solenoid will induce a current to produce south pole to attract the magnet moving away from it. Okay, so that is actually how it's being determined. Ignore the galvanometer's direction. The galvanometer direction in this slide is not accurate anymore because the galvanometer, this slide is KBSM syllabus. All right, the galvanometer will deflect towards the direction of the current flowing. Okay, so next that would be Lenz's law. All right, Lenz's law is actually to oppose the direction only. Now Faraday's law. Faraday's law talk about the magnitude. So here, the size of the induced EMF is directly proportionate to the rate which the conductor cuts through the magnetic field lines. So if more conductor cuts the magnetic field lines, higher EMF, higher induced current. If it moves faster, again greater induced current. If you have more number of turns, again greater induced current. And if you use a stronger magnet, all right, you would also induce a stronger current out. Okay, so up to here, I hope that you guys are okay. So I'm going to go back to the textbook again. All right, now let's see, insulator copper, blah blah blah. This is Faraday's. This part is talking about Faraday. So this is the direction of the induced current in a straight wire, which I already teach you guys using a Fleming right-hand rule. Okay. This part is actually explaining what I explained just now, all right, which is Lenz's law. All right, so we have a direct current generator and alternating current generator right now. The difference between the word motor and generator is generator will generate electricity out. All right, motor is actually to cause something to move. That's why it's called a motor. Generator is to generate electricity. So when we want to generate electricity, for example, all right, this one, what I want you to see is that when I actually press the green color button, look at the potential difference and look at the galvanometer. Okay, you would notice one thing: the galvanometer keeps on bouncing towards the right. All right, and when it bounces towards the right, for the potential difference, the current that is being produced out is always positive. All right, so what's the difference? Okay, this is for the positive one, which obviously this is a direct current generator. Alternating current generator right now will move towards the right and left, right and left. So the potential difference that you see here will move up and down, up and down, up and down. It has a positive potential difference and a negative potential difference. So what's the difference between um, direct current generator and alternating current generator? A part that it's being produced is either positive only or positive and negative. The biggest difference that I'm going to show to you guys is by putting it side by side. All right, the biggest difference comes over here. All right, on the left, this is a direct current. On the right, this is a alternating current. How can I see? Because direct current, this is actually called a commutator. You've seen this in the first part of electricity inducing magnetic field. This is a commutator, all right, and it will produce a direct current out. Slip ring, all right, slip SLIP, yeah, slip ring is two rings, and then the carbon brush is always touching the same ring. So I'm going to play this and you're going to have a look. All right, for alternating current, the carbon brush always touches the same ring. But then for a direct current, the carbon brush changes. A while, it keeps changes the ring that it's actually touching. All right, so the one on the left is a commutator. The one on the right is actually a slip ring. So the difference is commutator, they are just next to each other. All right, and there's a gap in the middle. But for slip ring, it is above and below. All right, it's not considered not side by side, it's above and below. All right, so this is actually the difference between a commutator and also, commutator and slip ring. Okay. So there's one thing that I want to inform to you guys is that in your textbook, at page 160. All right, page 160, do identify one thing. You can memorize this as a commutator alone. If you're going to memorize this calling it split ring, I think you would experience what I experienced. The one on the left is split, S-P-L-I-T. The one on the right is called slip ring. But alternating current, there's no word commutator. It's just a slip ring. But for direct current, it's called split ring commutator. All right. So in order to avoid confusion, I would suggest you just memorize it as commutator for direct current, slip ring for alternating current. Okay, that's how I memorize it. Now, this one, they didn't have it previously, so I would suggest you to put a remark over here. The working principle, the differences and the similarities between direct currents and alternating current generators. The similarities, both uses electromagnetic induction. Why? Because if you look back into the simulation, there is no power supply. It's just permanent magnet, rectangular coil, the ring, carbon brush, external circuit. There is no power supply at all. So it actually uses the working principle of electromagnetic induction. Okay. Next, the coil is rotated by external force. Okay. We will have to manually rotate. Think about your bicycle light. The bicycle light, the dynamo. Alright. Dynamo actually uses generator. So when you cycle, when you pedal on the bicycle, you are turning the coil inside the dynamo that actually supplies out electric current towards the light bulb in front at the bicycle there. All right. So the coil is rotated by external force. And then the coil will cut the magnetic flux inside the dynamo or the generator. And then it will induce EMF or induce current in the coil. The differences between direct current generator and alternating current generator is that direct current generator, the ends of the coil are connected to split ring commutator. But for alternating current, it's two slip ring. Right, so from now onwards, you hear Puan Leong saying commutator only. I'm not gonna say split ring because it's gonna twist my tongue whenever I talk about direct current and alternating current. Now, direct current generator, the two sections of the commutator will exchange contact with the carbon brush like this. All right, the carbon brush will keep on changing its contact with the commutator. But for alternating current, the slip ring are always connected to the same carbon brush. No matter how the generator turns, the carbon brush keeps touching the same slip rings. All right. And then for direct current, the output is obviously direct current lah. All right. It's a direct current generator ma. And alternating current generator, the output will be alternating current. There's positive and negative potential difference. Okay, so that is the difference and the similarities of direct current and alternating current. So one quick thing, because I noticed some of you in Form 5, you can't really understand when the question is asking you this. A part of stating the question of state the similarities and differences for DC generator and AC generator. Another word that they can use is actually compare and contrast. When they ask you to compare and contrast, it's actually asking you to state the similarities and differences. Okay, so this is one answering skills that I want to remind you guys. If they don't write state the similarity and differences, they will ask you to compare and contrast between direct current generator and alternating current generator. So they are actually asking for similarities and differences. Okay. Okay, I'm suddenly blank over here. All right, so that would end electromagnetic induction. Any question that you want to ask me? Got question? Please ask inside the tag inside the chat box. If you have printed this out, whatever that I didn't explain, it means that it's not really important. All right, or it's no longer in your syllabus, like this slide 41 until 42, it's no longer in your syllabus already, so that's why I don't bother explaining this. It's not that it's not important, but slide 41 and 42 is no longer in your syllabus. All right, up to here, are you guys okay? Okay, yes, no, hello. Thank you, Sarash. Okay, question, continue with transformer, or you guys want to do some exercises on electromagnetic induction? I think continuing transformer better. All right, I'm gonna let my voice rest for a few minutes. Then we will come back to talk about transformer. 5 minutes should be sufficient. So we come back at 9:05. Okay, for me to rest my voice for a while. I have one interesting question. How come I see Liu Junlim inside this Google Meet? Junlim, Form 4 so fast learn Form 5 stuff ah. Can I have a clarification? Is Junlim account being used by someone else or really the actual Junlim from 4 Alpha inside from 5 class? No response. Interesting. All right, is everyone back? Okay. Thanks for responding, Vitri. Okay, so we're gonna go into transformers right now. So I'm gonna be drawing some basic transformer because I've always taught transformer by drawing it out and explaining it directly. So let's just say that this is my transformer. I'm building the core of the transformer. Okay. So and then after that, so I hope everyone is back because I am explaining while I'm drawing this out already. Yeah. Okay, transformer, this is actually the core of the transformer and it's normally iron core. So if we want to make it even more, increase the electromagnetic inductions effect, it is to use a soft iron core because soft iron core easily magnetize and demagnetize. All right, so here we will have two coils, all right, two parts of a transformer. The first part is, it doesn't have to be on the left, sometimes it's on the right hand side, it doesn't really matter. All right, we have a solenoid over here on the left, and then this is actually the primary. For my situation case, this is the primary, this is the input. All right, why? Because here normally they'll say it's alternating current power supply, and it has to be alternating current. I will tell you why in a short while. And then when this is an alternating current power supply, and then at the other side, we will have our secondary. All right, we'll have our secondary coil coming out here. And at this part, this is known as secondary. It is also known as the output. Now, how do we see whether it's primary or secondary? Primary always have a power supply. Secondary got no power supply. All right, no power supply. What is connected here? It could be connected to a resistor. It could be connected to light bulbs. It could be connected to electrical appliances. All right, or it can also be connected to what some books will write as a load, electrical load. Electrical load means appliances, it can be light bulb, it can be resistor. All right, which means there's no power supply over there. Okay, now, so how does a transformer work? I'm already directly explaining the slides on how the working principle of a transformer. So initially, when the top part is positive, the bottom part is negative, current will flow through the solenoid, all right, from the positive to the negative terminal of the power supply. So when current flows here, all right, so magnetic field will be induced. All right, magnetic field will be induced whereby here will be north. All right, and when there's a soft iron core, it will magnetize. So the magnetic field that is produced at the primary coil will move throughout the core, all right, to complete the direction of the magnetic field produced. And what this thing will cause at the secondary coil is there is magnetic field passing through the solenoid. When there's magnetic field passing through the solenoid will reject the magnetic field that it feels. All right. So if this is the direction of the arrow coming in, so which means this is south coming in, here will produce a north. And let's see, my current will actually go here. My induced current will be produced inside the secondary coil. So this is when first half of the alternating current power supply, which is positive. Then what happened next is that it changes direction. The bottom part, because it's alternating current, it will actually change the power supply to negative part. So here is positive, here is negative right now. So when this happens, current will flow towards the opposite direction. Right, the green color lines right now to go back to the negative terminal, the green color one, and a opposite direction magnetic field will be produced by the primary coil, passing through the core, disturbing the secondary coil. All right, so when it actually, the magnetic field produced by the primary coil move towards the secondary coil, here this is when magnetic field will induce EMF in the secondary coil. So it will actually cause a current to be induced in the secondary coil. All right, so this is the whole entire working principle of a transformer. Okay, I hope that I explained that clear enough for you guys. So another thing that I just remembered and I want to add on is that at the primary coil, this is where electricity will in will create electricity will create magnetic field. While on the right hand side, at the secondary output or the secondary coil, the magnetic field will induce the current out. All right, so what is their common ground? Their common ground is this iron core. All right, the middle rectangular looking iron core. All right, so this is actually the working principle for a transformer. Okay, so what I've mentioned is this top part. So what I want to emphasize here is the higher order thinking question that they normally ask: why does the transformer does not work with direct current? Now please identify. If the question asks you why transformer cannot work with direct current, the answer would be, all right, a current is induced in the secondary coil only when there is a change in magnetic flux due to a change in primary current. So the only thing that can change the primary current is to use an alternating current. So direct current power supply only give a constant current, constantly positive direction current in the primary circuit. So a constant direct current whose magnitude and direction is constant will not be able to create a change in magnetic flux in the secondary coil. Therefore, electromagnetic induction cannot take place, all right, if we use a direct current. Do take note, this explanation is why transformer cannot work with direct current. If the question actually asks, all right, that's is where I'm going to start typing already. The main reason why I don't stop and let you guys copy is because this PowerPoint slide, I already sent it out to you guys already way before your trials. All right, so over here, if the question asks why a transformer needs to use AC power supply, then you have to mention everything regarding alternating current. Don't mention anything about direct current. All right, so why does a transformer need to use alternating current power supply? So the secondary coil will only be able to induce current if there is a change in magnetic flux created at the primary coil. The alternating current power supply will have a constantly changing current in terms of magnitude and direction. This will create a constantly changing magnetic field through the core. All right. So when they ask you why you should use alternating current, then just tell me why alternating current. Don't go and say bad things about direct current. If the question asks you why you should not use direct current, then you explain everything regarding direct current only. Don't go and explain alternating current. Okay? Please, please, please remember this. I think someone actually, not someone, a few people actually did some mistakes during this part. Okay? So I hope this one clarify with you guys. Screenshot this because I'm going to go to the next slide already. 5, 4, 3, 2, 1. Okay. Now is actually the number of turns of the solenoid. Okay, according to Faraday's law. All right. Me explaining, but everything is the same thing inside the slide again. Okay, according to Faraday's law, the more the number of turns, the higher the potential difference. So uh we have the primary coil and then we have the secondary coil. So as the number of turns increases, the potential difference at that coil will increase. If the number of turns decreases, the potential difference at that coil will also decrease. Okay, so when the number of turns at the primary is more than the number of turns of the secondary, which means the potential difference at the primary is more than the potential difference across the secondary coil, this is what we know as a step down transformer. All right, this is known as a step down transformer. If the number of turns of primary is less than the number of turns at the secondary, and the potential difference at primary, potential difference of voltage, okay, is less than the potential difference of the secondary, this is what we know as a step up transformer. Okay, so if the secondary has more number of turns or more secondary potential difference, then it's a step more. More means step up. If it has secondary has less compared to primary, that is step down. And please do take note, step up and step down, we look at the number of turns and the potential difference, not the current. All right, the current is not applicable for transformer. Okay, that's number one. Number two, okay, the formula in transformer. Because according to Faraday, number of turns is directly proportionate to the potential difference. So I have primary and secondary coil, isn't it? So number of turns at primary is directly proportionate to the number of turns of potential. Okay, let me use another method. Number of turns is directly proportionate to potential difference. So I want to put it at the equal sign. It will be number of turns over potential difference equals to a constant value. So because it's a ratio right now, so number of turns at primary over potential difference at primary, which is equivalent to a constant value, it would also be the same as the ratio of number of turns at the secondary over the potential difference at the secondary. Okay, so this is the first equation for transformer. I can rearrange this equation to let potential difference to be one side. It will be Vp over Vs. P is on top, right? So number of turns of P over number of turns at S. So here you can see that it is directly proportionate. Okay? No matter how I turn the formula, Vs over Vp equals to Ns over Np. This is also still acceptable. It's still the same formula. It's just rearranging it differently. But just remember the basic of Faraday, number of turns is directly proportionate to potential difference. Okay, so I hope that is clear with you guys. Now, if the question gives you the diagram, please do note in every single question, the front cover instruction already says diagram is not drawn to scale unless stated otherwise. So the number of turns, try to find from the question. Don't look at the diagram. The diagram can only tells you that it's a step up or step down. But if you want to know whether is it step up or step down, do not go and count all these lines. All right, don't go and count how many lines that the number of turns is being turned, because I did that last time now. Okay, it doesn't work that way. You have to look at the question, whether the question state the number of turns or not. All right, that is the accurate one, or else diagram is not drawn to scale. Okay, so I've already talked about step up and step down transformer. Up to here, are you guys all right? Yes, no, okay. Okay, I'm just very curious to find out one thing. Is Jun Lim still in? Seriously, he's still in eh? I'm wondering whether is it really Jun Lim listening to the class? Okay, now that is number of turns. So now I'm going to talk about ideal transformer. Throughout your whole entire syllabus for SPM, we do talk about ideal transformer. Ideal transformer, which means that all ideal transformer. All right, ideal transformer means all the power that is being input is actually being transferred to the output as well. All right, all the input power will go into the output also. All right, so here, input power and output power, how do we identify? Okay, is by using the formula that we learned in chapter 3 electricity. Power equals equivalent to current multiplied by potential difference. So because it's input, it means current input and potential difference input equals to current secondary or output and potential difference output. So it can be IP VP over IS VS. It can be I input V input equals to I output V output. Sometimes they go and write as I1 V1 equals to I2 V2. It's all the same thing. Input equals to output. All right. So this case, please memorize it as power input equals to power output. And then power is current multiplied by potential difference. All right. Try not to memorize any other way. I'm not going to show you the other method. All right. Because I used to get confused with that method. So I'm not going to tell you that other method. Okay. So that is ideal transformer. If it's not ideal transformer, it means that the transformer have a certain efficiency. All right. Efficiency formula is N. It's a symbol N, but the ending part is longer. Equals to power output over power input multiplied by 100%. That's why most of the electrical items outside you will see 99.9% efficient, 99.99% something. All right, they cannot say that they're 100%. Why? Because in the actual real life situation, when current flows through, there will be heat produced. If you're using a laptop or a desktop right now, you can actually touch the keypad or you can actually touch at the power supply there. It's actually heating up. Why? Because there's electricity passing through. They will induce magnetic field out. Then they have to do work in order to overcome all these things that is happening. So energy will be lost. All right, energy or power will be lost. So what does this mean? It means that the input power, in order for it to be 100%, it is actually the output power plus the power that is being lost. All right. So this is the one that causes it to be not efficient. All right. So let's see what else I have to say. Okay, I've already talked about power input, power output. Now, energy loss in the transformer. So we'll have to look more into the energy loss in transformer. So in a real life transformer, some energy will be lost, especially in form of heat energy, thermal energy. The output power is always less than the input power. Therefore, the efficiency of the transformer will always be less than 100%. So where does the energy loss go to? Energy loss is due to the heatings of the coil. It's due to the eddy current of the iron core. It's due to magnetization and demagnetization of the core, and due to magnetic flux, the magnetic flux. So, in order to explain further regarding the power loss, I'm going to go back to the textbook because it's more comprehensive over there. Okay, this is cost of the energy loss. Number one, resistance of the coil. The coil is made out of wire. All right, when it's made out of wire, the longer the wire, the higher the resistance. So the more the number of turns that is being over there, even though yes, it creates out more induced current, but the more number of turns also represents the longer the wire is. So when the longer the wire is, there is going to be resistance inside the wire or the solenoid or the coil. So what happens here that it will actually cause the current flowing to have resistance, and heating of the wire will occur. And when there's heating of the wire, that's where heat energy is being released to the surrounding. Very simple. You go and touch some of your wires, right? The thin wires, the one that you use to charge your handphone, normally you feel some heat over there. All right. So eddy current. Eddy current happens at the iron core. All right. Eddy current doesn't happens in the coil, the solenoid, or the wire. Eddy current happens in the iron core, because the iron core transfers the magnetic field from the primary coil to the secondary coil. So when there is magnetic field passing by, the iron core inside there will induce a current, and that current induced is known as eddy current. So eddy current will heat up the iron core, and again it will release heat energy to the surrounding. Hysteresis. Hysteresis is actually when the iron core magnetize and demagnetize. When it magnetize and demagnetize, there is energy supplied from magnetization. It's not fully recovered during the demagnetization, because there is going to be energy being supplied that is being created. So the difference of energy is transferred to the iron core to heat it up. If you don't really remember hysteresis, it's not that much of a if you can remember the hysteresis. If you don't, I think it should be okay. Now, leakage of magnetic flux. Leakage of magnetic flux is when by the primary current, the magnetic flux does not fully go to the secondary coil through the core, the iron core. All right, that is what it meant by leakage of magnetic flux. It goes somewhere else. All right, so how do you overcome this? All right, to overcome the resistance, they use a thicker copper wire. Why thicker copper wire? Because thicker copper wire means the diameter increases, the cross-sectional area of the wire increases. When the wire increases, excuse me, according to electricity, resistance equals to resistivity length over area. When longer wire to make more number of turns increases the resistance, then because we need the more number of turns so you increase the cross-sectional area by using a thicker copper wire this will reduce the resistance inside the wire. Okay, so use thicker copper wire so that the resistance of the coil can be smaller. Eddy current, in order to reduce eddy current, you laminate the iron core. All right, laminate the iron core that consists of thin iron sheets glued together with insulation glue. All right, so that it doesn't let the current to actually pass through. All right, it will insulate it. Hysteresis, we have to use soft iron core. Just now was just an iron core. Iron core magnetized and demagnetized, energy is lost. So in order to avoid hysteresis, you use a soft iron core because soft iron core requires smaller amount of energy to be magnetized. In order to avoid leakage of magnetic flux, you take the secondary core, you wind on the primary core, that all the magnetic flux produced in the primary. Okay, what does this mean? I know this is very difficult for you guys to understand. Now, in a normal classical transformer, the primary coil is on the left, the secondary coil is on the right. They don't share the same axis, but this will actually cause the magnetic flux to leak away when it is transferring through the rectangular core. So what do you do? What can we do? We take a rectangle, just a bar of soft iron core. And then after that, let's just say this is my alternating current power supply. I let this power supply coil at this soft iron core. So this is the axis of the primary coil. Then the secondary coil, which is connected to, let's just say, a resistor, I coil the same thing over the same axis. So they share the same axis. This will actually reduce the linkage of magnetic flux. They share the same axis. Secondary coil is wound on the primary coil. All right, so this is what it meant. All right, so that is actually how transformer loses its energy and how to reduce the energy. So please do take note. But honestly, to say transformer is a very famous question that keeps repeating every now and then. All right, so when you study on the transformer, chances for it to come out is actually quite low. But the next lesson that we're going to talk about, which is the this one, all right, electrical energy transmission and distribution. I think this one will come up more frequently compared to the transformer, but do learn and do understand in case that they come out the same question again. All right, so up to here, is there any other questions that you guys want to ask me?